Good afternoon everyone. So today we will discuss about an applications of an syntax character translation scheme. The main applications of an SDT are the construction of an syntax tree, type checking, intermediate code generation. So anyhow, in the next chapter you are having a intermediate code generation. We will see that how those STDs, that is L attributed STD and S attributed STD, can be used for the intermediate code generation, and also it is used for a type checking purpose also, and also this STD can be used for the construction of an syntax tree. So what is this syntax tree? Syntax tree is nothing but an conditional form of a parse tree. Suppose if I am having a parse tree, this is a parse tree for what? 3 star 4 plus 5. Suppose if I am having that grammar where E determine E plus T, T determine F and all the things, that expression grammar we are having, and suppose if this is the parse tree what we are having for the 3 star 4 plus 5, then the corresponding syntax tree for this parse tree is this one. So it is a conditional form of an parse tree, you can say. Then why we need to construct this syntax tree is, in some of the languages this syntax tree will be used as an intermediate representation of the code. So you know that there are many of the phases of the compilers are there, like lexical analysis phase, then syntax analysis phase, semantic analysis phase, then you will be having an intermediate representation. Okay, so intermediate representation, some of the languages they will use this syntax tree itself as an, not the parse tree. There is a difference between a parse tree and the syntax tree. Parse tree is for which phase? It is for an syntax analysis phase we are constructing the parse tree. Some of the languages will use this syntax tree as an intermediate representation. Okay, as an intermediate code representation they will use this syntax tree. Not all the languages, few compilers will use this syntax tree itself as an intermediate code generator. For a construction of such a syntax tree we are using the SDT. SDT is nothing but, all of you know that it used for the translation. Okay, like you will be having S attributed STD, L attributed STD and all those things. Okay, so now you will see how to construct this syntax tree. These are the application, and it is a conditional form of your parse tree. Now how to construct this syntax tree and what we are having in a syntax tree. Here when you will look at this one, you can say that you will be having a leaf node and you will be having a interior nodes and all the things. Each node of your syntax tree, okay, is implemented by using an object. Each node of your syntax tree is implemented by using an object. When I'll say the word object, then obviously you will have what? You will have a collections of the fields. You will have a collections of an fields. When I'll say it is an object, obviously you will have a collections of the field. So what are the fields we are having here is, suppose if it is a leaf node, if I am having a leaf node like this, then you will have one field called as an operand field, operand field, OP field it is called as an, and the other field is nothing but the lexical value that is provided by the lexical analysis phase. If it is a leaf node, so if it is a leaf node, how many field you will have? One is OP field, that is operand field, and the other one is the value field, that is the lexical value provided by the lexical analysis. If it is an interior node, so actually OP field is nothing but the it is an field which will label your node. Okay, OP is nothing but it is not an operator, it is not an operand, something like that. So OP field is a field which will label your node. If it is a leaf node, it will label that one. If it is in any of the interior node, it will label that one. So OP field is the one which is used for labeling of the node, and depends on how many child nodes it is having, so many fields will be there if it is an interior node. Getting my point? Okay, suppose if the node is a leaf node, you will have OP field. Along with the OP field you will have a one more field, that is nothing but the lexical value that is provided by the lexical analysis phase. If it is an any of the interior nodes like this, then you will have one OP field which will label that node. Along with that, you will have n number of the fields depending on the how many child it is having. If it has a 2 child nodes, then one is OP field and one node for this child and one more field for this child. So 2 more fields, one OP field and 2 more field for one child and one more child. So that is the how that interior node will be represented. So getting my point, each node of your syntax tree will be implemented by using an object, so which has a collection of the fields. Okay, and each of this node, interior nodes, will represent the construct, and their child nodes will usually represent the meaningful components. Okay, maybe a number, maybe some variable, some digit, or whatever it is. So that is about the syntax tree. Now we'll, along with the example, we'll see that how to construct the syntax tree. Now we'll consider the grammar for construction of an syntax tree. That the same expression grammar only we'll consider. So let us consider this grammar, that is a production and the semantic rule. So it is E determines E plus T. Just to differentiate it, it is at the head of the production and the E is at the body of the production. That subscript E1 is used, 1 is used. Then E determine E minus T, E determine T, and T determine parenthesized E, T determine ID, and T determine number. Now I'll write the semantic rules which are used for construction of an syntax tree. So whenever I am applying these particular production, the corresponding action has to be should takes place. Our corresponding rule has to be applied in order to construct the syntax tree. So here E dot node is equal to new node. So I am constructing the new node. How many fields? One is OP field, the other one is E1 dot node, and the other one is T dot node. Okay, as I told you, one OP field and the n number of the nodes fields depending on how many child it is having. So 2 child nodes are there, so it is and what is your OP field here? OP field is nothing but the plus. As I told you, what is that OP represent? It represent the label given for the node, so it is plus. So similarly for this E node, new node minus E1 dot node, comma T dot node. Same thing for this also. Then E dot node is equal to T dot node, and T dot node is equal to E dot node, and T dot node is equal to, it is a leaf node, correct? I told you how to do for a leaf node. So it is T dot node is equal to new leaf is the function. This is the function name. So it is a new leaf of ID comma, because it's an identifier. Okay, it is ID, OP field. OP field is nothing but ID, then ID dot entry. Entry is from a lexical analysis, whatever the data they are sending. So here T dot node is equal to new leaf. So it is number, that is the OP field now, and the lexical value provided by this one. Okay, why it is an ID dot entry here? Because we are taking the information from the symbol table entry. That's why it is id dot entry I have written. But when it is a number, directly the number 4, 3, like that we are getting it from the lexical analysis phase. So now this is the grammar what we are using for construction of the syntax tree. Now let us consider one example of an syntax tree. So example what I am considering is an a minus, it is a minus 4, a minus 4 star c, 4 plus c. Okay, so let us consider this particular example, that is a minus 4 plus c. Okay, so this is the expression what we are considering for construction of an syntax tree. Now we will see how to construct this syntax tree. So all of you know that how to write the parse tree. So just to derive this particular string, that is e dot node determine which one I need to apply, that is this one. E dot node is e1 plus t. Then this e will be replaced with e minus t. Then e has to be replaced with t and t has to be replaced with id. Okay, so I'll write this dot node because these are the nodes now. This is not an annotated parse tree. Okay, just I am writing a parse tree. It is not an annotated parse tree. Then t dot node. So here it is, t is replaced with you are having id. T is replaced with an id. Okay, now I'll see how to construct the syntax tree for this particular example. So and one more thing here, this particular whatever you are using this for the this grammar for the construction of the syntax tree, it works in the form of an bottom up approach. It works in the form of an bottom up approach. So that is initially t dot node. Okay, t determine id. So when it is a t determine id, what we are doing here, I am creating a new node. We are creating. Now I will write this one in the different color so that you can easily recognize that. This is an parse tree what I wrote. So now I will write the syntax tree. So it is t dot node. Okay. So here first which one I am applying, t determine id. T determine id, what we need to do when I am using that particular production, I need to create the new leaf node. So I need to create a new leaf node. What are the entry in that one? One is the id, means it is an identifier. Then you will be having an entry for what? Entry for an a. Entry from symbol table it is. It is an entry from the symbol table. So it is entry of a. Entry of an a. So when I am using this one, so I have constructed the new leaf node. When I am using this one, I have constructed the new leaf node, because when I am applying this one, I need to create a new leaf node. What are the parameters of that one, or what are the fields? One is id and entry into the symbol table. So from there we are getting the information about the a. So then after that one, so t is replaced with an e. So e determine t I am using. E determine t. So when I am using e determine t, what is my e dot node? It is nothing but a t dot node. That means here when what is my t dot node? It is nothing but this. Correct? Correct or not? So t dot node is nothing but this. So I will write it in a dashed lines. Okay. Now what is my e dot node? It is nothing but a t dot node. Where the t dot node is pointing here. So obviously what is my e dot node? It should be same, because your e dot node is nothing but a t dot node. So when I am using the production e determine t, E dot node is T dot node. What is my T dot node? It is a constructed a new leaf node. So now my E dot node is also pointing to this one, is also pointing to this one. Then here something is left. What is this? T dot node is equal to, it is ID number. So number. So number is nothing but the 4 in this particular example. So now I am using this T determine number. So when I am using T determine number, what we are doing? Again we are constructing the new node for that. So I will construct the new node for that. What are the parameter or the arguments in that particular node? So it is number. So it is an number. What is that number value? 4. The number value is nothing but the 4 in this example. So therefore when I am applying this particular this one, so what is my T dot node? T dot node will point to this one. T dot node will point to this one. Next what I have to do? So next one is we are applying this E determine E minus T. When I am applying E determine E minus T, I have to create a new node. So interior node. So I will create a new interior node. So what are the fields of this interior node when I am using E determine E minus T? So it is label is minus, and how many more fields you are having? 2 more fields. One will point to the E dot node. So where is the E dot node is pointing to this? Means it should also point to this. Now whatever the solid line I am writing, that is a syntax tree. Otherwise I will do one thing. Only that a syntax tree I will write it in a green color. Rest all I will write it in a black color. So T dot node is pointing to this. E dot node is pointing to this. And T dot node is pointing to this. Okay. So now whatever I am writing it in a green color, that is a syntax tree, final syntax tree what you are obtaining for this expression by using this particular SDT. Okay. Now E determine E dot. So here I have constructed the new node. So how many fields are there? 3 fields. One is minus field. Other one will point to the E dot node. What is E dot node? Where it is pointing. So that will point to the same thing. And the one more node is a T dot node. Where the T dot node is pointing? It is pointing to this node. So now it will point to this. It will point to this. Then I am using T determine ID. T determine ID. What I have to do? I need to create the new node for that one. So new node has to be created. How many fields? So T determine ID. How many fields? 2 fields. One is ID field. The other one is an entry field. Other one is an entry field. What is that value? C. Entry of an C. Okay. Then this T dot node now will point to this. Now which one? I am replacing E plus T with an E. Okay. So when I am applying E determine E plus T, what we have to do? We need to create a new node. So I will create the new node. How many fields are there? 3 fields. First field is plus. Next is points to E dot node. So where is, sorry, this I have not written. What is this E dot node? That newly one what we have constructed. So this will point to this. Okay. So now what is my next field? E dot node. So what is E dot node is pointing? It is pointing to this. Therefore this will point to this. What is one more field? T dot node. Where is the T dot node is pointing? It is pointing to here. So this will point to this one. So finally this is the syntax tree what you are getting. Final syntax tree. So this is the final syntax tree what you are getting for this particular expression by using this one. So this is how the syntax tree will be converted. This is how the syntax tree will be created by using the SDT. By using an STD. Any doubt? You can message me, or I'll show you one more example so that you will understand clearly. So nothing here, whenever we are using any of the production, what has to be done for that one, it will be there in the semantic rule. So apply that one and then construct the syntax tree. So only whatever is there in the green color, that is nothing but the final syntax tree what you are having. I will show you one more example by using, and whatever we are using it here, it is a what type of the grammar it is, and it is obviously an S attributed STD, because all your attribute value associated with a non-terminal, they depends on the value of their child node. So it is an S attributed STD we are using here, okay, for construction of what? For construction of an syntax tree.